Hi everyone, this is Dr. Muralidharan working as Associate Professor in the Department of Electronics and Communication Engineering from KPR Institute of Engineering and Technology, Coimbatore. I welcome you all for today's session on operational. The operational amplifier is a multi-terminal device. The pin diagram and symbol of IC741 is shown below. In the pin diagram of IC741, the pin number 1 represents offset null, pin number 2 represents your inverting terminal, pin number 3 represents non-inverting terminal, pin number 4 is minus VCC, pin number 5 is offset null, and pin number 6 is output, pin number 7 is plus VCC, and your pin number 8 is no connection. The symbol represents 5 terminals from the pin diagram. One is non-inverting terminal, another one is inverting terminal, and plus VCC, minus VCC, and output. The operational amplifier basically operates in two modes. You can call that as inverting mode and non-inverting mode. In the inverting mode, the input source is connected to the negative terminal and the output will produce a phase shift of 180 degree with respect to the input. In the non-inverting mode, it is performed by connecting the input source to the positive terminal and there will be no phase difference between the input and output. Let us consider the inverting mode. The input is connected to the negative terminal which is mentioned as VI through the resistor R1 and the output is fed back into the inverting terminal through the resistance RF and your non-inverting terminal is grounded. The difference between the inverting terminal and non-inverting terminal is represented as VD which is given as 0. Let us consider the analysis for inverting amplifier. For simplicity, we will assume an ideal op amp. The voltage available at the non-inverting terminal is 0 since it was connected to ground. So, the voltage available at node A is also 0. Now, we will measure the current I1 which is flowing through the resistor R1. So, I1 is equal to VI by R1. Since the op amp draws no current, all the currents flowing through R1 must flow through RF to the output terminal. The output voltage is measured V0 is equal to minus I1 into RF, where I1 is already given as VI by R1. So V0 is equal to minus VI by R1 into RF. So we can rewrite it as VI into RF by R1. The gain of the inverting amplifier is defined as output by input. So we are writing A is equal to V0 by VA, which is derived from the previous equation, which is equal to minus RF by R1. So this can be achieved with the help of nodal equation also. When you are applying the nodal equation at the node A, it is given as VA minus VA by R1 equal to VA minus V0 by RF. Since the voltage at the node A is equal to 0, so we can write the equation as A is equal to V0 by VA, which is equal to minus RF by R1. The negative sign in the gain equation indicates there is a phase shift of 180 degree between the VA and V0. Now let us consider the non-inverting amplifier mode configuration. Here the signal is applied to the non-inverting terminal, which is your positive terminal, and the circuit will amplify without inverting the input signal. So it is a negative feedback system as the output is being fed back to the inverting terminal through the resistance RF. Since the potential difference between the inverting and non-inverting terminal is 0, which is mentioned as VD is equal to 0, so the voltage available at the node A is the same voltage which is given as the input to the non-inverting terminal, which is VI. So here RF and R1 forms the potential divider. From the circuit, when you are measuring VI, it will be equal to R1 divided by R1 plus RF into V0. So we know that there will be no current flow into the op amp. So we can able to derive the V0 by VA, which is the gain of the non-inverting terminal, which is equal to R1 plus RF divided by R1. So simplifying the equation, we will get 1 plus RF by R1. Thus, for non-inverting amplifier, the voltage gain is given as ACL is equal to 1 plus RF by R1. The voltage follower is the extension of the non-inverting amplifier, where you will consider your feedback resistance equal to 0 and your input resistance equal to infinity. This modification will give you the voltage follower. The configuration of the voltage follower circuit diagram is shown in the figure, where the output voltage is equal to the input voltage. V0 is equal to A, both in your magnitude and phase. The output voltage exactly follows the change which is occurring in your input voltage. The use of unity gain circuit lies in fact its input impedance is very high and your output impedance is 0. So the voltage follower may be used as a buffer for impedance matching to connect a high impedance source to a low impedance load.